Good morning, everybody. My name is Davide Rossi from University of Bologna, and today I will introduce a secure RISC-V-based SoC for autonomous UAV navigation. This presentation is the outcome of a project between the University of Bologna, IDSIA Lugano, TII and Khalifa University from Abu Dhabi, and University of Modena and Reggio Emilia. So in the Internet of Things application, there are an undeniable great interest for autonomous unmanned aerial vehicles, thanks to their capability to navigate the environment and at the same time to sense, analyze, understand it, and provide meaningful information to the end user. On the other hand, there are some concerns regarding the privacy and security of these systems, which are often subject to cyber-physical attacks. In this context, the autopilot is a brain of a drone, and it is the component which allows the drone to navigate autonomously. And this autopilot is usually composed of a flight stack and a flight controller hardware. There is an increasing trend due to security reasons and also, let's say, increase of widespreading of information to provide open source hardware and software stacks for autopilot. In particular, PX4 is a powerful open source autopilot flight stack, which includes all the software necessary to make different kind of drones fly, and it is very flexible and support several operating systems such as Nuttx and Linux. PXOC is an open source flight controller, so it is the hardware support, or at least one of the hardware supports on which the PX4 autopilot can fly. So the latest release of the standard is called FMU V6. It hosts an STM32H7 microcontroller, and it runs PX4 on Nuttx real-time operating systems. So some of the limitations of this system are related to the fact that there is no support for Linux in STM32H7 microcontroller, and on the other hand, this platform is not fully based on open source hardware. So the goal of the proposed project is to present the first fully open source flight controller SoC for UAVs and replace then the STM32H7 microcontroller in PXOC, providing support for both Nuttx and Linux operating system, and at the same time improve performance, efficiency, and security of the system, and design a scalable and versatile architecture able to deal with different use cases, such as flight control for standard drone, single SoC flight computer for nano drones, or implementing also communication stack, which are necessary for this kind of application. The project started this year, and one of the main milestones is the plan for a tape out in Q1 2023 in 22 nanometer global foundry process. The SoC architecture is composed of, let's say, three main blocks. One host subsystem, including two 64-bit Linux-capable processor, one secure subsystem providing the security layer to the SoC, and one accelerator for implementing different kind of workloads, such as deep neural network for different applications. On the host side, we exploit the CV-A6 processor from Open Hardware Group and ETH-Z. One of the features that are exploited in this project are the capability to boot Linux. So it has a full support for MMU and TLB, data instruction cache, hardware page table worker, and the support for machine, hypervisor, supervisor, and user privilege modes. In order to implement a cache-coherent environment around CV-A6, we exploit the OpenPython network on chip from Princeton University in order to improve the performance of the system, providing the capability to support a dual OS such as Nuttx and Linux concurrently. On the peripheral side, the system implements a 64-bit EXI interconnect from PULP project, which is extended with the peripheral and memory protection plus an on-chip SRAM, and the full set of IOs which are required to make it compliant with the FMU V6 specification, PCB specification. In addition, due to the quite large requirements in terms of external DRAM memory, which come from hosting an operating system like Linux, we implement an hyperbus controller from PULP project in order to support up to 512 megabyte of hyper-RAM or 80 memory, which are quite cheap and low cost IoT memory. And finally, we have a root of trust, which is based on the OpenTitan IPs from RISC, providing secure boot, secure firmware update, and security preventives to the rest of the system. In order to be able to deal with dedicated workloads which require quite heavy digital signal processing, we enhance the platform with a parallel programmable accelerator from PULP project. It consists of a cluster with 8 32-bit RISC-V cores with a wide set of extensions for deep neural networks and other kind of general purpose signal processing algorithms. And we extend this cluster with TLLB for efficient communication with the host subsystem supporting virtual memory and implementing the translation between virtual and physical addresses as an IO MMU. As a use case for this system, we propose an elderly or child monitoring, which consists basically on a pose estimation deep neural network, and includes also concerns related to security, such as encryption of sensitive data before transmitting it to the network, and secure firmware update. The pose estimation deep neural network is called PULP FrontNet, and it's based on proximity neural network. So the original neural network was including more than 6 megabytes of parameters and was running on an Intel Core i7 platform. So in order to fit this neural network in the, let's say, tight memory footprint of the proposed architecture, we implemented some quantization, modification of the network topology, and an exploration of the size of the model, which is proposed here. And I will talk about this in the next slide when I will explain the result. So the workflow of mapping neural networks into the SoC is supported with open source tools as well, such as Nemo and Dory, and both the technology Nemo and Dory and the neural network are on GitHub and can be used for deploying deep neural networks on PULP-based systems. In this slide, we propose an evaluation of our work. On the left, we compare our work in terms of regression performance accuracy with respect to the original proximity network. And as we can see, basically, all of the proposed configurations of the network provide quite good results in terms of accuracy and can be used to real deployment on the field, as demonstrated by the video you can click on and take a look. So we first implemented the network on COTS hardware, exploring the design space and seeing that we can achieve up to 110 frames per second within 100 milliwatts on a pulp shield based on GreenWave's technologies GAP8 processor, which is a COT hardware. And we will expect in our proposed SoC to be able to run the same network with 135 frames per second, consuming less than 87 milliwatt with the cluster enabled, and deliver in general up to 2.6x better peak performance and 4 times better energy efficiency, and most importantly, enabling security for secure navigation of autonomous drone and secure transmission of relevant information and secure firmware update. So thanks a lot for your attention. I will be available for answering your questions.